Hi, everyone. Today, right now, I'm going to go over a chapter 4 review exercise to review some of the main topics that we've talked about in chapter 4. And this will be easily summarized in this review question on page 198, number 5 and 6 on energy efficient. So if you look to the left here, you can see that I have the question pulled up right here. This is on page 198 of the textbook, okay, and you can also get it on the ebook, which I have open right now. So for us, if you have the textbook, it's right here, page 198, number 5 and 6 right at the top here. Okay, and for those of you who are trying to get to the ebook, remember if you're in Connect Math from Canvas, if you just look to the right and click over here, you'll get to the ebook. Okay, so number 5, and let me see if I can make it a little bit bigger, is about energy efficient. A sample of, too big, a sample of 10 households was monitored for 1 year. The household incomes in $1,000 and the amount of energy consumed in 10 to 10 joules, okay, were determined. Okay, so the results follow. Okay, so we got income on the first row here and then energy on the second row here. Okay, and then we have some parts here that we want to follow here. Okay, A, B, C, D, and then in number 6, we use the same data here, and we got A, B, C. So we got 7 parts. Okay, so let's get started here. Okay. So in number 5A, we want to compute the least squares regression line for predicting energy consumption from income. Okay, so we want to figure out basically, we want to figure out that y equals b0 plus b1x, okay? Okay, this equation here, okay? Or y equals a plus bx, okay? Now, depending which format you want to keep with, okay, this is what our book does. This is the equation of a line, okay? And then this is what our calculator does, okay? And then I'm going to write it really small here. On the side, we have our y equals mx plus b. This is what you learn in algebra, the y equals mx plus b, okay? So this is what we're ultimately computing, okay? Remember that, and in my last video when we did this, we talked about the thing that's next to the x is the slope, okay? So these are the slopes here, okay? We're not going to look at this one anymore, okay? These are the slopes here, the thing next to the x, and then the things by themselves, that is the y-intercept, okay? So we really just have to figure it out. This is a job for our calculator, okay? So I'm going to pull up the calculator here. Okay, and I'm going to go to the home screen here. And remember, the way we do this is that, well, we got to enter in the data into our calculator here, okay? And then we also have to decide which of the data is x and which is the y, okay? So we'll do that in just a second. Okay, so first we're going to put this into our calculator. If you know how to do this, maybe pause the video and put it into the calculator and then see if we get the same answer. Okay, so I already have it preloaded into here because just to save some time. So remember, you go to stat edit and then you want to enter one of the variables into one list. So this is my income list here. And then you want to enter the other variable, this is energy, into another list, okay? Then we're going to go to linear reg, so stat calculate, okay? And then option number 8, okay? So remember, option number 4 is linear reg, but to match our book, we're just going to go to option 8, okay, linear reg. Okay, the difference is that this lin reg a plus bx matches up with what the book does, okay, a plus bx, okay? And the convention is, maybe I'll just write this down in just a second, just to remind you, in the stats world here, okay, b0 is that y-intercept, okay? okay? And then B1 is the slope, okay? Okay, this is what happens in a statistics class. Okay. Okay, oops, I think I spelled statistics wrong. Oops. Okay, anyway. Okay, so now that we have ln_reg, okay, we're going to go here, going to calculate. Okay, so we have to make sure, I don't know why it says P here, but we want to make sure that the X list is our, well, X list is going to be our X's and Y list is going to be our Y's. Now, which one's X and which one's Y? Well, let's take a look at the problem here. Well, it says here we want to compute the the least squares regression line for predicting energy consumption from income. So we're predicting the energy income from income. Let me say that one more time. We're predicting the energy consumption from the income. Okay, so that means income is going to explain or predict the energy consumption. Okay, so, oh, sorry, let me move the calculator here. Income is going to predict the energy. It's going to explain the energy, okay? So this one here is going to be our explanatory variable, okay, our predictor variable, and then this is the response, okay, the outcome, okay? So remember, just to remind yourselves, we have all these words that mean the same thing, okay? So, let me see if I can find that paper that has the words that all mean the same thing. Okay, here we go. So remember, the explanatory variable might affect the response variable, okay? The treatment affects the outcome, the independent affects the dependent, okay? And now we added some extra ones. The predictor, or the X variable, might affect the Y, okay? The response, the outcome dependent, okay? And the question is asking us, oops, let me leave this here. The question is asking us for the line that predicts energy from income, okay? So, and that's what we have here. Income is predicting energy, okay? Great. So that tells us which ones are X and which ones are Y. Our X is going to be the income, our Y is the energy. Okay, so X is income, Y is energy. So this will be second L1, because that's where my income went, and then L2 is the Y, okay? So now, again, once you have your X and your Y, we ignore frequency, and then this stored reg equation, we just ignore it, and we go to calculate. Okay, and you can see, well, part of the reason that we chose this ln_reg option number 8 is so that a plus bx, the b is the slope in statistics, okay? So really, the b's are slopes in statistics, which is kind of annoying because, whoops, it's kind of annoying. In algebra, you learn that b is y-intercept. In statistics, okay, we're back. Sorry about that. So the b is the slope in statistics, and then the a, or the b0, this is often called b0, is the y-intercept. Okay, anyway, at the end of the day, our regression line is just y equals, so y equals a plus bx. Okay, well, the a is 2.882. Okay, so usually the convention is you take 3 decimal places, but follow whatever the book says. The book doesn't really say anything here, so I'll just take 3. Okay, so 2.8823 plus, all right, bx, so that's going to be a 0.889, just a 9x. Okay, and that's the regression line equation. Okay, so I know I just said like a bunch of stuff here, okay, but at the end of the day, you're just computing this y equals a plus bx. The one thing that you have to think about is, what are we doing? Predicting energy from income, or the other way around, predicting income from energy? So you have to think about which one's the explanatory, okay, explanatory or predictor, okay, oops, I spelled predictor wrong, predictor, okay, this is the explanatory predictor, okay, and then this is the response, okay. or the outcome. Okay, remember we have all these words that mean the same thing. But at the end of the day, you're just computing this guy here, okay? Okay, so we just finished A, okay? Letter B here, we want to construct a residual plot, and we want to verify that a linear model is appropriate. Okay, so letter B is a topic that falls into 4.3. Okay, and since we're not covering 4.3, 4.3 is optional, we're going to omit it. Okay, so this is a 4.3 topic. Okay, remember this is extra credit, I'm going to omit it. Okay. But if you're interested, maybe in a follow-up video, I will sort of talk about what the residual plot means. And this is kind of an important thing to think about. One thing to remind ourselves is that the methods that we are doing in chapter 4 is really good when things look like a line. So we need to, before we even sort of do what we're doing here, doing this problem, using the regression line and doing the next few problems, we should actually verify that what we're seeing looks like a line. Okay, the scatter plot for this data, we should verify that it looks like a line. Okay, and it does. We will do that later on. Okay, when we get to number 6. Okay. Okay, so maybe I'll just write here, we should verify that, okay, income versus energy scatter plot looks like a line. Okay. Okay, so it looks like a line or is close to a line. Okay, and that's what this section in chapter 4 is really good at. Remember our topics here on this little post-it note cheat sheet. Okay, so 4.1 we talked about R. This is the sample linear correlation coefficient. 4.2, this is the least squares regression line. And then 4.3, this extra credit topic is the coefficient of determination. These are all good when the scatter plot looks like a line. Okay, but when the scatter plot doesn't look like a line, we have to pause. Okay, so we'll come back to this later. The point of this in 4.3 is that it's important to look at your data. Okay, so again, this is extra credit. This is extra credit topic, so we will omit it. Okay, so letter C here. Letter C, if okay, so I'm going to set this aside. Letter C, if two families differ in income by $12,000, by how much would you predict their energy consumptions to differ? Okay, so this is here, we're talking about differences, we're talking about change. Okay, so one of those words that you might want to put into your list here is difference and change. These mean the same thing. Okay, these are words that mean the same thing. Difference, change. Okay, you might hear make a difference, make a change. Okay, you probably have heard that before. Something you might not think about when you go to the grocery store. Okay, when you pay with cash, you're asking for your change. Like if I pay $17.23 for some toilet paper or something, okay, and I pay with a $20 bill, okay, I want some change back, okay, the change is the difference, okay, so these two words are actually, they're really the same thing, okay. The point is for letter C here, let me put the calculator away, is that we're talking about changes here. So if two families differ in income by $12,000, by how much would you predict their energy consumptions to differ? Okay, so really we, in this question here, like we did before, and if you haven't watched the other video with the crickets and temperature, make sure you watch it. I'll link it in the description below. But we are given something and we want to find something. Okay, what we are given is that two families differ in income by $12,000. Okay, so we're given, really, well, you're given a difference. A difference is a change. Remember, difference is change. So, and this is income. Income is what we called X, okay? So income is X, that's what we called X here. So we're really given a change in X, and the change in X is $12,000, okay? Okay, so I just wrote down 12 because X is really income. X is income in $1,000, okay? So really I should put income in $1,000. Okay, so this is really 12, okay? Okay, so and remember this triangle X means delta, okay? And what we want to find, well, how much would you predict their energy consumptions to differ? So we're asking for a difference in energy consumptions. That's just a change in Y when we translate. Okay, so we're looking for a change in Y. Okay, so change in Y. This is what we're trying to find. Okay. Okay, so if you're not okay with this, make sure you look back at the other video, okay? But the point is, once we know what we're given and what we want to find, you have to find the relation between what's given and what you want to find, okay? And the relation here is straightforward here. It's just the slope, okay? Remember, the slope is this rise over run business, okay? Which translates to change over Y, change over X, okay? Okay. So the point is, okay, well, we want change in Y. So one way you can really memorize what, kind of how to do these problems with slope is that, okay, well, the change in Y, okay, sort of if you multiply both sides by the delta X, then you get, the delta X here, you get slope times delta X. Okay, so if you go ahead and multiply both sides by delta X here, okay, so this cancels out, okay? So that's where this comes from here. Okay, so really the answer here is just, okay, take delta X, which is 12, and multiply by the slope. The slope is the thing that's next to the X here, okay? Okay, so answer delta Y is equal to, okay, well, the slope, which is 0.889 times 12, okay. Okay, and this is where if you need your calculator, I'll pull it back up. Okay, by the way, as we're doing this, remember, if you don't have a graphing calculator, Texas Instruments is making this emulator available for free for students and myself, okay, during this transition to online education. So check Canvas if you want to see how to get the link. Okay, this is also available for Chromebooks as well. Okay. Okay, so hopefully that's okay there. Now, something I will sort of just pause for a second that might happen here is that you might get slightly different answers. You might get slightly different answers here if your rounding conventions are off. Okay, so make sure you follow whatever the book says. Okay, so here I took 3, but when you round, okay, so maybe I'll just put here in red, follow instructions, rounding instructions. Okay. Okay. Okay, so whatever the book says, if it says 4 decimal places, then take 4. If it says 3, take 3. In practice, what you do is you take as many that you need. Okay, so I just took 3. That's just what I usually do. Okay, so this is what I have here. Okay, great. Let's move on here. Are we done with 5? Oh, we're not done with 5. We have one more part here. Okay, we want to predict the energy consumption for a family whose income is $50,000. Okay, so this is another one of those questions where we're given something and we want to predict something. Okay, so this is part D. Okay. Okay, and we want to, what do we want to do? We want to predict the energy consumption. Okay, well, energy, remember energy is Y. Okay, so if I could, I would write down maybe a Y here, but I'm not sure if I can do that. I know I can highlight, but I don't know if I can write down a Y here. But yeah, we want to find Y, basically. We want to find Y energy, okay? That's what we're predicting, okay? And we're given, well, what are we given here? We're given, for a family whose income is $50,000, okay? Well, income is X, okay, so that's income here. Okay, so remember, this is all available from part A when we set up the least squares regression line. Okay, so for predicting energy consumption from income. Okay, so we're predicting y from x, and that's basically the point of this section here. If you remember from our slides here, we have these questions. Let me see if I can bring them up. So if we're in modules here, and I'll go down to the slides, class 13, 14 slides. So, I mean, this section is about, again, relations between variables, quantitative numerical variables here, but we want to answer questions. Okay, so let me see if I can find those questions that we want to answer. Okay. Okay, so given two variables x and y, is there a linear correlation? So we haven't even talked about this yet, okay? We will in the next problem in number 6, but right now we're kind of doing question number 2 here. If we know x equals something, can we predict what y is, okay? Okay, so that's what we're doing here. So let's go back to the book here. Okay, so, what are we doing? Given x, find y. Okay, well, what's the relation between x and y? It's exactly this equation here. Okay, so all we have to do is plug the given into here and then simplify, and we have our answer. Okay, so, well, y, and typically, sorry, what are we giving here? Given x is $50,000, so 50. Okay, so again, remember x is 50 because this is income in thousands, okay? Okay, so y of 50 is just, okay, we just plug in x. Okay, so 2.883 plus 0.889 times 50. Okay, and that's all we have to do. We just plug in that. Okay, so now to do this on your calculator, well, you just have to do 2.883 plus 0.889 times, so parentheses if you want to, 50, or you could just use the times. Okay, and then you get 47.333. Okay. So this one's much straightforward. We just have to interpret the question correctly. The question is, predict the energy consumption for a family whose income is $50,000. So really you're predicting the y for a family whose income for a family whose x is $50,000. Okay, so remember each of these pairs of numbers here, so maybe I can highlight one of these. Each of these pairs of numbers here is a family. Okay, so this is a family whose household income is $96,000, and the amount of energy they use in a year is 98 10 to the 10 joules, whatever this is. Okay. Cool. All right. So if you need to, feel free to pause and just reflect on the last few questions before we go back, or before we go to the next one, which is number 6. Okay. So FYI, what we've done so far here in number 5, this is really a 4.2 question. So maybe I'll write that down. This is a 4.2 question. Okay. Okay. So. All right, so number 6 now. Again, number 6, we're using the same data, so we don't have to change our calculator. We want to compute, so part A here, we want to compute the correlation coefficient between income and energy consumption. Okay, so this is R. Okay, so we're just finding R. Okay, so really, there's not much to do here. You just have to remember that R is correlation coefficient, okay? So correlation coefficient is the short name, okay? But the long name is linear correlation coefficient. It's actually sample linear correlation coefficient because this is coming from a sample. This is all coming from sample data here, okay? Okay, so once you know what correlation coefficient R is, you just have to go to your calculator and find R, okay? So unfortunately, it's not here anymore, so we just have to calculate it again. Okay, so remember that we want option number 8, okay? And then we want to calculate this. Okay, So, and it's this number here, okay? And you don't have to write down the entire thing, just follow the rounding directions, okay? So typically I take 3 places, so it's going to be a 0.95, okay? And then you can see that, okay, well now it's 9, but then we only want 3 places, so you check the 4th one, okay? This is above 4, so that means this 9 has to go up. But 9 going up means that it's 0, okay, it goes up to 10, but that means that, okay, this 5 has to go up to a 6, okay, so this is 9597, it actually goes up to 0.960, okay, if we want to round to 3 places, okay, this is for 3 places. Again, follow the directions, okay, so this is round 3 places. Okay. Okay, so I'm going to actually cross this out now because this is the answer here. Okay. Okay, so that's it. Nothing else to nothing else to it. That's what R is. Okay. Part B says compute the coefficient of determination. Okay, the coefficient of determination. Okay, so again, this is a 4.3 topic again. Okay, so this is an extra credit topic. So again, if you want to just I encourage you to read 4.3, and if you have time, do 4.3. 4.3 is actually kind of important for those of you who need statistics moving forward. So if you're going to psychology or biology, or you might need it in the field later on, this 4.3 is actually important. But it's something that will also be covered in your future classes as well. But I want to give you a preview by giving you this extra credit opportunity. Okay, so basically the coefficient of determination, it's just R squared, okay? So it's literally just the square of this, okay? Remember, square, you just multiply. What's the square? You just multiply by itself. R squared is R times R, okay? That's what the square is, okay? So literally you just have to multiply this by itself. But really we need to multiply this before it was rounded by itself. Luckily the calculator does that for you. So the R here is, or sorry, the R squared is this here, okay? 0.921, okay? Just like with variance and standard deviation, you really have to have the standard deviation. You have to have the entire thing and then you square it. Otherwise you're gonna have a rounding error. Okay. Okay. So this is it. This is the coefficient of determination. Now, so this is computing. This is not that bad. You literally just square, or you read it off your calculator here. I think the thing that you have to think about is what is the coefficient of determination, and what is this? What is going on here? And that's kind of outlined in the next question, part C again. So now part C, this is again an extra credit topic here. Okay. And this is where you have to do a little bit of thinking and about what do these numbers mean. And I'll say a little bit here, but then in another video I will sort of outline and sort of just summarize what 4.3 is about if you're interested. But to motivate it, going back to our questions, okay, is question number 3, how good are our answers to question 1 and question 2? Okay, so question 1, given 2 variables x and y, is there a linear correlation between x and y? Well, the answer to that question is just r. Okay, is the r close to 1, basically, or close to -1? Okay, if it's too close to 0, remember that means that you don't have correlation. Okay, and if it's close to 1, either +1 or -1, then you have a strong linear correlation, okay? And the dots have to look like a line. And then question 2 is about, can we predict one variable from the other? Can you predict y from x? Can you predict, in our example, energy from income? Okay, and then 3, well, you're making predictions here. So you're making predictions, you have to understand that we're not going to be right, okay, when you make a prediction. Okay, so the question is, okay, how good are our predictions here? Okay, and that's where this r squared comes into play. The r squared is important because it tells us a percentage of sort of the a percentage of the total variation that is explained by the least squares regression. Okay, so that's really what r squared. Okay, so r squared tells us a percentage here. So really the answer to this is kind of move this over 2 decimal places to the right here. Okay, the answer here is 92.1%. Okay. Okay, so that's something a 4.3 is all about, is that, so, oops, let me move this out of the way, okay. R squared, this is the coefficient, this quantity here is called the coefficient, okay, coefficient. So many big words. Determination. Okay, so coefficient of determination, okay. And it's a fact, this is sort of a fact here, and maybe I will say a few words about it in another video, okay, that r squared equals, okay, sort of explained variation divided by the total variation, okay. Okay, and this has to do, this variation has to do with the sort of the variation between the y's for a given x, okay? And some of it is explained by that least regression line, by this equation here, y equals b0 plus b1x, or a plus bx, okay? Some of it's explained by this, but some of it's not, okay? So anyway, look at 4.3 or the other another video later on for the explanation to this. But that's it for now. We've just finished all 7 parts. Okay, these 2 questions here. Okay, so before we end for this one, I just want to sort of now pause and talk about, well, we didn't even look at the scatter plot for this, okay? So just to go back to here, we should really verify that the scatter plot looks like a line, okay? So now I'm going to show you on sort of a feature, and this will be on Canvas if you want to play around, sort of the scatter plot here. So on the left here, here's that scatter plot, okay? And to our surprise here, maybe it's not a surprise, because we computed the correlation coefficient. The correlation coefficient is 0.92, sorry, that's not the correlation coefficient. Where's the correlation coefficient? It's 0.96, okay? So if you computed this, you should be thinking, okay, it's positive and it's close to 1. Okay, this is positive, close to 1. So these dots should be forming a line, okay, or very close to forming a line. And as you can see, it's kind of close to forming a line here. You can see that these dots here in particular are very close. And then if we maybe add this one's a little far off. But like if you kind of ignored these 2 here, okay, I'm not sure if I can hide them right now, it'd be very close to a line, okay? Okay, so this is our scatter plot here, and we have a positive correlation. So that means as the income goes up, as the x goes up, income goes up, the y also goes up as well, energy, okay? So if we're making more money, then it looks like we're also using more energy, okay? But remember, we can't say that that income causes the energy, okay? We can't say increased income is going to cause increased energy. We just have a correlation. We have a relationship between the 2, okay? And in part A, what we did was we computed this regression line here, okay? I'm going to show the regression line here. The regression line is, oops, am I going to show it here? Whoops, that's the wrong one. Is it this one? Nope, those are the squares there. Where's the regression line? Here we go. Here's the regression line. This is that line that we wrote down. Okay, this is that line here. Okay, and as you can see, so you can kind of see here, these are the answers to our questions here. Okay. Yeah, these are our lines. This is our line here. Okay. And what we predicted in part D here, okay, is, okay, well, we took x equal 50, okay, so x equals 50 here, okay, so I'm going to, Okay, and then we plugged it into our equation here, which is, I call it G in here. Okay, and that predicted a y of about 47.333. Okay, so it's a little bit off because of the rounding here, but it's not too bad. It's about 0.02 off. Okay. Okay, so that's what this is predicted here. Okay. Great. Okay, so this is really what we should actually verify before we start doing these methods. So if you're going into the business and you want to use linear regression, so by the way, what we're doing here is all called linear regression because the lines are the dots are forming a line here. Okay, so we are going to use a linear correlation and use the linear regression line. Okay. If your dots were forming a curve, then you want to use nonlinear methods, but we won't talk about that in this class here. Okay, and it's kind of important to make sure that the dots look like a line if you're going to use the methods that are being done in this question here. Okay, so as the last sort of thing, just to sort of emphasize this point here, we should really look at your data. You have to visualize your data, so you want to make a scatter plot before we even do any of this stuff. Because if this stuff is all good, but if our dots don't look like a line, that could be problematic. Okay, and here's sort of a classical example here. This is, I'm not trying to say this person's name, so I think I'm going to butcher it here, but and Scambe's, okay, and Scambe's quartet here. Here we have four data sets here. You got 1, 2, okay, 3, 4, and you got 4 sets of x's and y's. So you got x and y here, and then you got x and y here. Okay, oops, x and y here, and then you got x and y here. So you have 4 sets of bivariate data. You have 4 pairs of x's and y's, okay? And it turns out that the statistics for these x's and y's are very much similar. They're very similar. So one surprising thing is that if we were to calculate the r here, they're all the same. All the r's are the same, okay? But if we look at their scatter plots here, okay, here's the scatter plots, you'll see that the scatter plots look completely different. Okay, here in the first data set, we have positive correlation. In the second one, we have kind of positive, but it's non-linear. Okay, but I wouldn't say it's positive because it goes down here. Here you kind of have positive, but you have this outlier here. Okay, so go away. This is the third one. And then here you kind of have a positive, but it's not really positive linear. It's like that pennies. Remember the weights of the pennies? You have a cluster here, and then you have one dot here. Okay. It turns out that the R, the sample linear correlation coefficient for all 4 of these, is the same. Okay, so you can see here, for all 4 of these, the mean of x's are the same. Okay, and then the R right here is the same. Okay, very similar here, and even the correlation, the coefficient of determination of linear regression, r squared, which in some books they use capital R squared, is also the same too. So and you can see also from here that the least squares regression lines are all the same. So the methods that we are doing in chapter 4 are only really good for these ones here, the first and the third one here. They're not going to be good for something nonlinear or something that's like this. Okay, this, I'm not sure what a name for this is, but it's not a curve. It's not connected like this one in number 2 is. Okay. Anyway, so that's it for this one. So make sure you look at your data. That's the last thing I'll end here. Okay. See you later.